Ladies and gentlemen, my name is Jiri Hyks, and I will be talking about utilization of incineration bottom ash in constructions. I come from a small consulting company called Danish Waste Solutions, where we specialize in offering expert services within the waste management and management of resources, with the emphasis on the environmental aspects. We have many years of experience with bottom ash as well. Here are some of our bottom ash relevant references. As an introduction, what is bottom ash? Incineration bottom ash is well known globally under different abbreviations. In Europe alone, there are some 15 to 19 million tons of bottom ash produced annually, and this amount is expected to increase in the future. Rather than a waste, bottom ash can be looked at as a potential resource for two different types of resources. Metals, obviously, ferrous and non-ferrous, which gives together roughly 10 to 15% of the mass, and the mineral aggregates, which is roughly 80 to 90% of the mass. And this is the part which we'll be looking at today. So what is the properties of bottom ash aggregates? First of all, fresh bottom ash after quenching has high pH, shows high leaching of salts and metals. It's volumetric and not stable. Hydrogen can be generated, etc., which means that fresh bottom ash is generally not suitable for direct use and should be pre-treated before being used. There are different sorts of pretreatment, passive and active. The most used passive treatment is so-called aging. The active pretreatment could include removal of metals, could be washing, removal of fine fraction, addition of some binders, and also thermal treatment, all depending on what are you going to do with your bottom ash afterwards and what are you trying to achieve. The considerations regarding bottom ash pretreatment are that the choice of the pretreatment depends on the intended application, meaning I could have washing, I could have crushing, I could have removal of whatever, if it makes sense. And we should remember that always some high recovery rates of certain materials may be actually outweighed by high energy consumption and potential downstream environmental burdens. So therefore, looking at the whole management from a life cycle assessment point of view may be beneficial. Also, a holistic approach is necessary when assessing bottom ash processing, because in the end, we would like all fractions of the bulk ash material to be managed one way or another. So what are the utilization options for bottom ash aggregates? Let's now assume that we have a bottom ash which has been treated, meaning it has the metals have been removed and the material has been stabilized to some degree. And we have different options what to do with the material. The most common one would be construction of landfills or landfill cover. Others would be unbound construction aggregates, and then using the bottom ash in some products, using the bottom ash in cement production, using the bottom ash in production of foam glass, etc., etc. What is really important to realize here is that these options have different stage of maturity and acceptance, and there is a different potential for management of the bulk mass, and also different costs and environmental impacts. So these options are not equal. And the most used option worldwide is the utilization as unbound construction aggregates. And this is what we will be discussing further. So what are the pros and cons of this option? The good thing is that bottom ash has good mechanical properties and can replace virgin materials in specific engineering applications. The bad news is that bottom ash is not inert, and it also contains mainly inorganic substances that may be potentially harmful to the environment if the bottom ash is not pre-treated correctly and or if it's not used correctly. And the main potential risk is in the leaching of elements from the bottom ash, specifically salts and trace metals. By leaching, these elements can be transferred into percolating water, and migrate through soil and pollute the groundwater resources, for example. Therefore, the pretreatment aims at reducing the leaching of the contaminants, while the application conditions for bottom ash should be regulated in such a manner that these unacceptable impacts on groundwater will be prevented or limited. So, what is our experience with using bottom ash as unbound aggregates? It has been tested in many countries, in different setups, under different conditions. There is just a short list of references from one of the articles, but there are many, many more available from different countries. In a real life, the situation is a little bit complicated because on European level, at least, there is no harmonized criteria for the use of bottom ash as unbound aggregates. Several countries have developed their own national guidelines and regulatory quality criteria for the use of bottom ash in unbound applications. In most cases, the quality criteria include limit values on both the content and the leaching, and are also accompanied by certain conditions on the use of the material. Often there is more than one set of rules reflecting different conditions, and of course, less restrictive limit values are corresponding to more restrictive use conditions. The figures here is example for France, where bottom ash could fall in two different categories, and based on the results of the testing and compliance with those two sets of limit values, it can be used in two different applications. What is really important to realize here is that the different national limits and criteria are not comparable from country to country, because they have been developed under different premises and different considerations. As said, the situation is different in different countries. If you want to get even more confused, I suggest you look up this article from 2020 by Dominik Blasenbauer and colleagues, who have actually provided an overview of the legal situation and current practice of utilization of waste incineration bottom ash in Europe. And there you get information about the permitted fields of application, the requirements on total content, leaching, etc., etc. So if we go to Denmark, in Denmark, Denmark has a long history and experience in utilization of bottom ash. Already in 1974, 4,000 tons of bottom ash were used under a 9,000 square meter parking lot. Monitoring of leachate from both the bottom ash layer and the gravel layer beneath the bottom ash was included. Of course, back then they were only monitoring a couple of elements, but it was the start. Since then, there's been numerous projects carried out. Leaching tests have been developed. Legislation has been constantly developed and updated. People realized that in order to assess the risk for the groundwater, one needs to rely on the results of leaching tests and not on the results of the solid analysis. Today, the environmental part of the utilization process is regulated by a statutory order, while the technical part, meaning how to build from bottom ash, is covered in several documents from the Danish Road Directorate. Today, there is approximately 600,000 tons of bottom ash generated in Denmark from more than 20 incinerators. 99% or more of this mass is actually utilized as unbound aggregates. So landfilling is not considered an option for IBA in Denmark, and it has been done this way for years. And it's important to stress that this whole process is an ongoing process. If there are new pollutants, we should include them. If there are new modeling approaches, we should include them as well. So it's not a static process, it's always developing. This slide just gives an overview over the functional requirements and the environmental parameters which are monitored in Danish bottom ash prior to the utilization. The functional requirements are those similar to a stable gravel, because bottom mesh is replacing the gravel, basically. And the environmental parameters are determined for each 5,000 tons of bottom mesh and include measurements of solid content and measurements of leaching. And because we have done this for many years, and because we test each 5,000 tons, we have thousands and thousands of data points, so we can basically see long-term trends as well. So if we have the results of the leaching test, we can classify secondary aggregates, including bottom ash, in 3 different categories: category 1, 2, and 3. Danish bottom ash is typically complying with the limits for category 3. This is the one marked in a green box. For this material, for material which complies with the limits for category 3, the allowed applications are subbase in roads and paths, foundations, and fill on the floors. There are some technical limitations to these applications, meaning the thickness of the layer must be less than 1 meter. There should be tight cover to reduce infiltration. There should be minimum distance from drinking water wells. The whole body of bottom ash should be placed over the maximum groundwater level, and so on. If for some reason your bottom ash sample does not comply with category 3 limits, or if the technical conditions cannot be fulfilled, a permission to use or utilize the bottom ash may still be granted based on a specific risk assessment procedure under the Environmental Protection Act. And this is typically the case of highway ramps, where the maximum filling height is much higher than 1 meter. So some real-life experience and data. This figure shows a cross-section of a real road with heavy traffic, which was built in connection with expansion of Copenhagen's of a harbor in Copenhagen. The test road had 6 different sections where different combinations of materials was used in the construction. There was crushed asphalt concrete, there was stable gravel, there was bottom ash, and there was sand. And we can see sections F1 and F6 marked with green. Those are the reference scenarios, meaning these sections were built using the typical or natural materials used in these reference scenarios or anywhere else in Denmark. The other sections, F2, F3, F4, and F5, had bottom ash or included bottom ash in either unbound subbase or unbound base, or in case of F4, in both unbound subbase and base. The road was monitored thoroughly. It's a closed road with heavy traffic in 1 lane in, heavy trucks, empty trucks going out. So we have both heavy and light lanes. It's a closed area, so each truck is weighted and registered on the way in and out. So one has pretty exact idea of the load on the road. And between 2012 and 2020, regular measurements of Young's modulus in all different parts of the roads were carried out, together with monitoring of rutting and smoothness, all in order to assess the quality of the road based on the materials which has been built from. The conclusions of this project is that it has been confirmed that bottom ash can be used in an unbound subbase of heavy stressed road, up to 900 trucks a day. Surprisingly, for some people, the E-modulus of bottom ash was actually higher than that of stable gravel. It was also concluded based on the measurements that the bottom ash can be used in traffic roads with a stress class higher than T4, which is the normally allowed application in Denmark. Here T6 was tested, meaning even heavier trucks or heavier traffic was on the road and the road wasn't damaged. And most importantly, the results for the field F4 and F5, where bottom ash was used in the base layer, indicated that the material has qualities high enough and ought to be considered in construction of the base layer, meaning it could be moved from the subbase into the base. Thereby, there is a potential for replacement of high quality or more expensive materials. So, of course, new full-scale test projects are in preparation to confirm these results as well. Here is a funny example of an ongoing large-scale project where a new 4-kilometer bridge will be constructed in Denmark. In connection with the construction of, on both ends of the bridge, a highway ramps must be constructed alongside a train ramp. The bottom ash will be used only in the highway ramp, as the quality of the material needed for the train ramp is different. So Danish Road Directorate, which is the investor, intends using 250,000 cubic meters of bottom ash, which is something around 430,000 tons of bottom ash, as unbound aggregate under the asphalt or clay, with the maximum filling height up to 11 meters, which is more than what is allowed normally for the category 3 applications without permit. So that's why a specific risk project assessment was done by a consulting company, Corvi, who has calculated release of metals and salts during construction as well as use phase, and as well as after 500 and 1,000 years. The major result is that the metal front movement is roughly few millimeters after 125 years. So the project got a green light and the bridge is expected to be finished in 2023. Here is the example of some potential future applications of bottom ash. It's called bitumen stabilized material, BSM. The story is that already in the 90s, the use of bottom ash as aggregates in asphalt mixtures was investigated or tested in at least Denmark, Norway, UK, and USA. But back then it was given up because the porous nature of the bottom ash led to higher consumption of the bitumen compared to the natural aggregates. So the whole system was more expensive. Today, however, with the increasing press on recovery of resources or recycling, a bitumen stabilized material method can be used, is used for asphalt. In this method, milled, crushed, and salted asphalt from old pavement is heated and mixed with some percentage of foam bitumen, little cement, and little water. And this mixture is then used as ordinary hot asphalt mix. People ask questions whether this can be used for bottom ash, and some lab tests have been done in order to test this hypothesis or question. The test results were promising in the sense that very high E modulus of the bitumen stabilized bottom ash was measured. And the question is now, could this technique be used to create bitumen stabilized bottom ash, which will be utilized in the road base layer? So again, moving the bottom ash material from the subbase to the base layer towards the more expensive materials. So the take-home message here is that pre-treated bottom ash has good mechanical properties, and it can replace virgin materials in engineering applications, such as typically subbase in roads, maybe base in roads, highway ramps, and so on. However, bottom ash also contains inorganic substances that may be harmful to the environment if they leach out. meaning the bottom ash needs to be treated sufficiently and needs to be used under proper conditions. And the main potential risk is related to the release of salts and trace metals into percolating water, thereby polluting the groundwater. So the pretreatment of IBA should reduce the leaching of contaminants, while the application conditions should ensure that the unacceptable impacts on environment are prevented. So these two things must go hand in hand. One cannot have one without the other. The use in unbound applications specifically has proven feasible worldwide, as both the functional and environmental requirements are okay, provided that the metals are separated, the bottom ash has been aged or weathered, and it is used in specific applications under specified conditions. Importantly, it should be noted that the use in unbound application is inexpensive compared to all the other methods, is very cheap, and it's applicable to the bulks of IBA, meaning there is no additional fraction remaining which needs to be handled afterwards. So this way, it really helps in preserving natural resources and saves landfill space. I would say, although we have this option and we use it, there might be new, more advanced management options that may move IBA upwards in the waste hierarchy. And we shouldn't be afraid of exploring these new options. However, these new solutions should always be assessed in a life cycle perspective, meaning including also end of life. Thereby, one would account for all associated potential environmental impacts and consumption of resources. Thank you for your attention.